Okay, and I've got my video showing. Welcome everybody. Welcome to the IEEE Lehigh Valley Section of the IEEE Computer Society. Our talk tonight is going to be on a comprehensive introduction to computer graphics programming. My name is Angelo Mastercola. I'm the chair. And guess what? You're in for a special treat because our vice chair, Nav Sandhu is giving the talk. Let me open up my share my presentation here. Is it showing?
Yep.
Okay, excellent. I'm gonna go through this as quickly as possible to maximize the amount of time for Nav. So again, welcome. I would ask that everybody self-mute so that we minimize background noise. But maybe it's not as much of an issue with Microsoft Teams, but you might choose to mute or block your video potentially for bandwidth reason. May not be as much of an issue. We are, however, I want to emphasize we are recording this for posterity, for archival purposes, for educational purposes, etc. So I just want you to be aware of that. I'll make some brief additional announcements and then give a brief abstract description of the talk and a biography of the speaker. Again, I want to make this as quick as possible. This is the second talk of 2020 as part of the charter for reviving the IEEE Computer Society section here in Lehigh Valley. These are the new officers. I just introduced myself and Nav. Nav is going to be giving the talk tonight. Okay, I guess this is a review. Last month's talk was Here Comes 5G, an excellent presentation that Dr. Sundar Vedantam gave. Tonight it's computer graphics programming, as I mentioned. And if anybody listening or anybody either would like to give a talk that would be appropriate for the Computer Society or know somebody that might, please do contact me. Here's my email, and my email is also in the should be in the notices you got, or at least in the event page that you went to register. If you need PDH credits, current IEEE membership is required, and please email me if you're requesting PDH credits, and it's also something you can request when you register. Membership renewal for IEEE opened up on September 8th. You're invited to renew for those that are members. I wanted to say that membership is not required for for viewing this talk, but by all means, if you'd like to be able to get notice and information about a variety of additional topics and talks and other benefits from IEEE, we basically encourage you to consider IEEE membership. It's really worth the price. And also, should it be the case that there's any specials or circumstances at the IEEE.org website, and when you log in, if you're a member, and maybe even at the main website itself, there are special considerations, special discounts for special circumstances, whether it's being retired, low income, unemployed, etc. So, welcome you to check that out. Okay, tonight, the official schedule, we can have some flexibility around this based on something that Nav and I were talking about a few minutes ago. Nav's going to start the talk at 7. That is, if I hurry real quick, at 7:06, and then talk for about an hour. Then we'll have Q&A. I guess Nav might want to schedule a little bit of an interim Q&A, which is fine with me. And now on to the abstract and then the biography, and then I'll pass it over to Nav to begin to talk. The computer graphics programming is a new field that's different than traditional software side of computer graphics, and this focuses entirely on algorithm, computer science, and implementations of those algorithms. Now, while the goals are still the same, computer graphics programming includes computer graphics work, although it has more focus on application and program development of multi-level and multi-core systems at its simplest level, getting a CPU and a GPU to work together using programming, primarily using C++, though other computer language implementations are available as well. Okay, now I'm going to move on to the biography of the speaker. Navjot Sandhu is a contractor, programmer, computer graphics specialist, and CEO, CTO, and creative lead of his company, Subquantum Businesses, an education and entertainment software company where he is currently working within Microsoft, Intel, NVIDIA, and Autodesk developer programs and networks. Subquantum Businesses is also, Nav is also a graduate of Microsoft's entrepreneurial program, BizSpark now, Microsoft for Startups, where he was learning to use and leverage Microsoft Azure and build his business around. He works on supercomputing, parallel processing, multi-device and multi-core processor principle programming using CPU and GPUs to create high-end solutions for e-learning, as well as creating state-of-the-art computer graphics, animated film, and video game studio, in addition to other interactive multimedia products. The studio will create its own content in high fantasy, science fiction, and eventually sports games, as well as turn-based role-playing video games. So you're not only going to learn some technical stuff here, you might actually be entertained a little bit. Nav attended Lehigh University 1999 to 2003, then completed his degree at Colorado Tech University online with the inception of its software engineering online curriculum. Colorado Technical University recently has become one of the most awarded online universities, including multiple awards and acknowledgement from the U.S. Armed Forces. He currently holds a Master of Engineering degree in Technology and Information Management and Master of Computer Science and Human Computer Science from Carleton University in Ottawa, Canada. He recently completed a thesis in 3D UIs, user interfaces, building upon the past successes of 2D user interfaces in the realm of business, user productivity, and science, as well as others. And Nav also proudly volunteers with the IEEE and the LVEC. He's currently webmaster of the IEEE Region 2, which includes the Lehigh Valley. There's the website. He's vice chair of the IEEE Lehigh Valley Computer Society, as I introduced him at the beginning. He's also the past chairman, vice chairman, and current webmaster of the Lehigh Valley Engineering Council. Again, there's the website. His email's included and his basic address. So with that, I think you're in for a treat tonight, folks, and I'm going to hand it over to you, Nav. Let me see. Do I need to unshare, or is that something you take care of?
I think I can do that. So you just have to approve it.
I think I just stopped sharing there.
All right, same difference.
Yeah.
Really quick, I'm just gonna do a quick fix on there was a typo there as far as, so it should be human computer interaction. That's the field of like user interface elements. That's my second master's degree, is Master of Computer Science and Human Computer Interaction. And just wanted to correct that really quick, pretty important. And with that, I will start the presentation. And thank you, Angelo, for that wonderful introduction. I really appreciate it.
Sure, you're welcome. Thank you for presenting.
You're welcome. My pleasure. Okay, and okay, so welcome everyone. The IEEE Lehigh Valley Computer Society presents a comprehensive introduction to computer graphics programming. Okay, so the tonight's presentation is going to consist of an introduction, a history and computing industry significance, modern technologies and companies, the GPU and operating systems display subsystem, vertices, indices, triangles, primitives, and scenes. Then we're going to do a programming overview, how it works, including the graphics pipeline. Then we're going to have a small Q&A for those that have any questions. We want to clarify anything if anyone has those kind of questions. Then after that, we'll do a programming requirements map overview, which is basically if you're interested in entering the field or know someone who is, like what kind of stuff do they need to know. And Then we're going to look at a quick sample application, a very simple application. And then we're going to look at some advanced applications usage. We're not going to go through any advanced code or anything like that. It's just going to be a quick discussion and a web page about like what kind of things people are doing. And then lastly, we're going to have some fun and look at some video on the latest state of computer graphics as far as and advances in what GPUs are being used for and the direction that they're headed in. And finally, we'll have a last Q&A. So computer graphics programming involves programming code to produce visual graphics, either to be displayed on a monitor or to be created, like for example, an image and saved on a file, either in computer memory or persistently on a file system. So modern computer graphics involves all those aspects of programming involving interacting with hardware, software, firmware. So it's like hardware, software, all the things that need for things to work together, all that kind of stuff. So there's different sections and there's different groups. This presentation is mainly involved with the actual programming of it as far as an application developer would be concerned. So in GPUs, for those that don't know, are graphics processing units, are specialized coprocessor units. It's just like another kind of CPU, but it's specialized to handle a specific kind of data. And that's what's mainly used when people are referring to computer graphics programming. GPUs have evolved into a variety of form factors and configurations that satisfy needs in different aspects of the computing industry. So there's different types of GPUs and chipsets and so on and so forth that have different power requirements, have different capabilities, etc. And so they could be in a mobile, desktop, server, and or in an embedded form factor. Like I was saying before, the difference between a GPU and a CPU is a GPU has hundreds to thousands of computing cores, utilizing especially made for concurrency and parallel compute methodologies and principles, and usually whose architectures and underlying components allow for streamlined computation of vector and matrix math-based data. So that's what I was saying before about it's a specialized kind of CPU, and it's the type of data it's mainly meant to process is vector and matrix math-based data. And so all this is going to basically shed a light to what's the big deal about that loading screen when loading a video game and this and that. So hopefully we'll be able to figure that out by the end of the presentation of what exactly does that mean. So quick history. So video cards, GPUs started out as video cards, and not just video cards, but specialized display technology that only did a specific thing as far as displaying characters on a screen. And some of the companies that were involved were ATI, 3DFX, SGI, Namco made arcade machines, and so they did a lot of work there as far as having specialized video units inside a computing side by side with a computing unit. And software-wise, what interacted with the GPUs was technologies from OpenGL and Microsoft DirectX, namely in the 90s. And eventually, some of those companies were bought up or they were merged together with other companies, but the people involved pretty much remained the same, and they continued to be in the industry. And so then OpenGL and DirectX are still around, and the main focus of these the kind of work that everyone did was focused on concurrency, parallelism programming, multi-core, multi-threading, multi-node, high performance computing, all those kind of principles of parallel computing. So the modern companies are the following. So it's like the main players are Intel, AMD, NVIDIA, and as far as hardware is concerned, and AMD bought ATI, and now they're AMD ATI, and on the software side you have things like OpenGL, Kronos Group, Metal, and Microsoft DirectX, as well as Vulkan. Kronos Group was made from various people from SGI, and they're very much involved with a lot of the work being done in computer graphics. Metal is a new kind of Apple used to use OpenGL exclusively, and now they've made their own. And that's the Metal there. And so there's two kinds of basic methodologies when it comes to software and computer graphics programming. So you have the OpenGL, DirectX, Vulkan, Metal, and WebGL. WebGL is like OpenGL, but used in a web browser. And these technologies are primarily used for application development. Then you have another subset of programming called OpenCL, CUDA, Direct Compute, and they are used for a lot of engineering and sciences, and that's a specific type of programming called GPU programming. So the GPU, while it's a graphics card, kind of has two subsections as far as how it's used and utilized. So challenges that programmers or people in the industry, what they work on is like, how do they get this kind of amazing technology to us? So they have to work on scalable and parallel design-oriented software and programs at all kinds of different levels in the software stack. They have to make it so it's affordable and economical for a worldwide audience, and performance. They have to worry about performance as far as like being the best and getting the most out of the chipsets. They have to worry about getting it to work on multiple operating systems. So it's a lot of work there. And then the big one is manufacturing, is like, how do they get all those things in scale delivered to their customers and to meet the demand of the global customer base. So again, primary usage, as I mentioned before, is rendering and or ray tracing. And so that's like when they use the APIs that I mentioned before, like OpenGL, DirectX, Vulkan, or OpenCL, CUDA, and Direct Compute. What are they actually doing? So one of them is actually you're displaying some kind of image on the screen, or again, you can save that to a file, or you're doing some kind of computation or GPU computing where you're processing data, but you may not necessarily be displayed on the screen at the end of the day. It'll just be, you can process the data and then push it back to the CPU or in storage or in a database or something like that. So again, to summarize, modern use cases are science and engineering simulation, cloud computing with big data and number crunching, hardware accelerated user interfaces that have more expansive set of capabilities than a regular user interface would, gaming, interactive applications, virtual reality and augmented reality. And a big one is image and video processing. GPUs were really and are still readily used because they have a huge computational advantage over regular CPUs as far as image and video processing is concerned. So they're used a lot for that. So let's take a look really quick at the GPU and the operating system's display subsystem. This is very important for application programming. So over on the left-hand side, so there's different operating systems involved, and there's like Windows, Linux, Mac, so on and so forth. They all generally basically follow the same structure, but and so there's different examples here, but you can basically get a good idea about how it pretty much works. So over here you have the over here on the left-hand side we have an example from Microsoft and Windows. So there's two modes here, user mode and kernel mode. Kernel mode is what the system is using and what it has access to. The user mode is what the user has access to as far as being a programmer or using an application and so on and so forth. So you have in the kernel mode, you have a direct graphics subsystem. What that does is there are drivers from each vendor, like there's different kinds of graphic cards from different companies. So basically each device has to have its own set of drivers that are going to run on the operating system that allows applications and programs to access that particular piece of hardware. That's what a driver does. And so the DirectX graphics kernel subsystem communicates with the driver, and that driver communicates with the GPU. And then so the DirectX graphics kernel subsystem basically gives access to specific features of the GPU, as well as managing all its internal states and internal windows that are going to be running up on the screen when you run an application and so on and so forth. And here you have like the Direct 3D runtime, which is what when application programmers use an API, that API is going to make a call to something called a runtime, which is what is going to be accessing which is going to be communicating with the kernel subsystem, and so on and so forth. So the reason why they have that is because for security purposes and as well as extensibility. So that provides a lot of features that is important in computer programming in general, and follows those kind of principles. And that's as much as I'm going to discuss about that, because that's like a whole nother lecture. Now, if we look at the DirectX API, this is the API programmers use. And there's also like an OpenGL API, a Vulkan API. These are all different technologies, like different kinds of ways that different companies are allowing people to interact with the GPU to draw something on screen or to perform some kind of function. So basically, the Direct2D and Direct Write, that's like for 2D graphics, like two-dimensional graphics, and for text writing. And then you have Direct3D for working with a mesh. DXGI works with interacts with the hardware on the GPU itself, and so on and so forth. They all have different features, and they all perform some kind of function like various programming APIs do. Here is the Linux graphics subsystem. So here you have the same kind of thing going on. You have your Linux kernel, you have your GPU and graphic memory, CPU and main memory, and the Linux kernel has access to that. Then you have different drivers from different manufacturers. One's from NVIDIA, one's from AMD, and they're accessing that subsystem with specific rights. Then you have your game engine or what have you, and then there you're going to use a specific version of a programming API that will have different features and capabilities, and they're going to communicate with the GPU using those APIs. So that's what this is showing here. Another important thing, like I mentioned before in the Windows subsystem, that the thing that manages all its windows and applications and programs that you use on a daily basis, that's called a desktop manager. And so Windows has its own, which is proprietary, but in Linux, because the things are open source, there's different things available, and they did things a slightly different way where, like different groups of people can create their own kind of window manager. And the main one in Linux is X11. That's showing right here. It's called the X11 system. That basically creates the window, and as well as other user interface elements, and so on and so forth. There's a new one out recently called Wayland, which is competing with X11. And X11 has been around for many, many decades. But so they created Wayland to take advantage of the latest advances in the Linux kernel development, which has also been evolving through many years, and now has reached a pretty good state. And so they created Wayland to take advantage of all those latest features, whereas it's very difficult to do that with X11 because things have been done a certain way for a very long period of time. And so now there's some competition going on, and we'll see what happens there. Okay, so now we're looking at the data, and so there's vertices, indices, triangles, and primitives. Now, this is basically going to explain the basic data that graphics programmers use to create some kind of picture on the screen, like a mesh or a game character or a movie character or whatever. Like what are they composed of? And so that's what I'm going to show now. And I'm going to switch really quick to a website. Okay, and so here is primitives. And so primitive is basically, so the GPU, it's like I said before, it's optimized and it's an enhanced version of a CPU, and it can do certain kinds of things very good. Like that's why they designed it, and that's why GPUs are popular. So here you see the different kinds of things that it can do. Like on the left-hand side here, it says primitives, and you have point lists, you have lines, and you have triangles. And guess what? That's all they have. So that's the basic nuts and bolts of how they do everything. So it's like you either have a point, you either have a line, or you have a triangle. So now if we look like, so this cube is composed up of triangles. And at the base level, that's what's being created. I know it's crazy, but that's the way it is. And so here's a sphere, and it's actually just composed of triangles. And so if you go here to triangle list, what's happening here? So this is the data that's how those shapes that you saw before are being composed. It's all about numbers and math. So it's right now we're passing in some data, and it's saying, hey, I want to make a triangle. Here's the points I want you to use in space to draw those triangles, and so on and so forth. For 3D coordinates, like, so you see here is a float of X, Y, and Z. So the format that has to be passed in is X, Y, and Z. So and so on and so forth. And that's basically the gist of it. So that right now we're seeing a triangle list. You also have things like triangle strips. These are connected. So when you pass in the data, same data is passed in, but it's a different mode. It connects those triangles together to form some kind of patch, it could be a rectangle. You can make any kind of shape, and that's how meshes are created. We're going to see more examples of that later on for those that have any questions about that. And you have a triangle fan here. This is just another way of representing or ordering the numbers that are in the interpreting the numbers that are passed into the GPU. So you can pass in data, and you can choose different modes. Say, I want this to be interpreted as a list, I want it to be interpreted as a triangle strip, or I want it to be interpreted as a triangle fan. And so they did this because it has different computational and geometric qualities that allow different shapes to be rendered on screen, either faster or better or smoother, and so on and so forth. There's different qualities and properties involved with each kind of shape. Okay, now I'm going to go back to the slides. Okay, so and then that brings me to scenes. So a scene is basically what you see on the screen, but scenes are created by programmers. The GPU doesn't know what a scene is. It's a CPU side kind of thing, or like a programming kind of construct that manages or helps the programmer or coders or team of programmers manage all the objects they want to see drawn on the screen. So you saw those triangles before. When you go into computer programming, that's structuring it into objects and different kinds of things that are visibly or pragmatically discernible by the programmer. And so then it's up to the programmer to create a structure that basically creates a scene. And scenes can be different things. It could be objects or meshes, like we were looking at before. There could be a light. And it's not a light in a real sense, like it's not a physical light, but it's simulating a physical light. Or it's and the next one's a camera or an environment. An environment is also an object or a mesh, and it's also simulating and then you have environments basically are like what the other meshes, like characters or an object or an item, what are they sitting in, or what are they contained in. And then you also have cameras. Again, it's not a real camera, but it's like a mathematical construct that's representing what a camera would physically do in the real world. Also, when you have meshes and data, some meshes are dynamic objects, or some are pre-generated objects. Basically, you can create a math program that generates that data in real time on the computer when the program is running, or you can create the like an object ahead of time in a DCC tool, like for those that have used like Blender, or there's Autodesk 3ds Max or Maya. Basically, those are tools that allow artists to create different kind of meshes. And so those once those meshes are created, they are stored in a file format that is basically loaded by the computer graphics program. And so those are pre-generated types of objects. And just give me 1 second here. I have to check my notes. Okay, so basically, so here's a look at something called the computer graphics pipeline. So this is the beginning of the programming overview. So once you have that data, those numbers I was talking about before, like that makes up the triangles and so on and so forth, how does that going to help the GPU? like how does that interact with the GPU? That's what we're discussing here. So before, they used to have something called a fixed function pipeline where you could enter that data and it would just straight go to the GPU, and it would you could do some drawing. You could create some points on the screen. You could, I'm sure everyone's done something like this. You enter in the vertex data and it creates lines on the screen or colors and this and that. It's pretty much very straightforward. But so then objects are 2D or 3D geometries are, so they're drawn on screen using positional data and color information. And that's what basically the gist of, like a base level format of what's required to get something drawn on the screen. You need to have positional data of the geometry, and you need to have color information. So what happened with the fixed function pipeline, they would use that color information and positional data, like I was saying, and they would just enter it manually. So now they have something called a graphics pipeline with the emergence of something called a shader. A shader is another type of code that, like in addition to the primary programming language like C++, and it's like a C++ language, but basically it only runs on the GPU. And so what they did is they developed something called the graphics pipeline where you have multiple shaders sending data from one stage to the next, and each shader is like a stage. And on the right hand side here, you can see like the different stages that are available. You have the vertex shader stage. You have something called the hull shader, which has to do something with tessellation, and same thing with a domain shader. All these three are connected. Then you have something called the geometry shader stage. And then you have something called a rasterizer stage. The rasterizer stage isn't programmable. That is something built into the programming API. After that, you have the pixel stager stage, which is programmable. So everything you see here that's a rectangle, that's non-programmable. Everything you see that's like circular, that is programmable. And then you have your final state that once it goes through all, you enter in your data, and once it goes through all these stages, and it doesn't have to go through all of them. I'll explain that in a second. But once it goes through this graphics pipeline, it outputs the final image or set of data that you'd want to see displayed on the screen. Okay, and so then you have like the data format like we were discussing before. You have vertices, indices, UV coordinates, textures. You have topology and coordinate systems. And something really very important as far as graphics programming goes, it's all done as far as like you want to make it run as fast as you possibly can. So it's called low latency application development, very similar to what fintech and quantitative trading is, as far as like code methodologies and like optimization and making it like perform as best as you can. So we do a lot of research on techniques, algorithms, data structure, code management. It's like everything you can do to make it run faster, do it, and or something like that. Okay, and then so really quick, I'm going to show you about something, a quick demo. So just give me 1 second. Okay, time. And okay, so just give me 1 second, sorry. Okay, so previously I discussed something called tessellation. This is a very important thing, and it has to do with a specific kind of shader. It's called tessellation shader, which is a recent development in the past decade. It wasn't available before then, and like on GPUs specifically, or at least not automatically. Can you guys see this? Can someone confirm that they can see the two triangles on the screen, or the triangle and a square on the screen?
Yep.
Okay, great. Okay, so this is what tessellation is about. So before I was saying, okay, we pass in triangle data. So here's a triangle, and it composes this shape. And so there's shape on the left-hand side, a shape on the right-hand side. So that gives you a certain finite amount of detail. Once you have this detail, you'd probably say, oh, wow, that looks great, right? But so what in programming, we want as much detail as we want, as much detail as possible as far as data goes. So the way we there's a feature called tessellation. What it does, and it's a huge part of computer graphics research, like what people work on, is like how to improve this. And so this is called a base mesh, where that's the data that the programmer passed into the GPU. So what tessellation does is it's going to split this up into even finer triangles, but you don't have to pass in all those triangles manually. It does it automatically. So let's take a look at that really quick. So what that did is it divided the mesh into an even further subset of data. Like, so it made it even finer. So basically, it's kind of like sampling. So that, which is, we're gonna take a look at something like that later. Like when you do sampling of a signal, the more samples you have, the better. So same thing here. So what they're doing is, what tessellation does is, you have like a base mesh, then you want to make it finer, right? So that's what tessellation does it automatically on the GPU, and it's great. And so really quick, here's another look of why that's important. This is basically a different view of the same concept. So here you have this model that someone made. It's like a scary monster thing. And let's take the tessellation all the way down. So here we have no no tessellation basically. And you have some kind of displacement map on top of it saying, or this is the base version, this is the base mesh, and it's saying there's something else on top of it called a displacement map. The displacement map is what gives it its like features, like little crevices and things like that. And that's outside the scope of this introductory course. But anyway, just so basically you'll get the gist of it as far as so this is without tessellation. And once you increase the fine level of detail, that data that's in that displacement map is now actually able to deform the mesh properly, as according to what the displacement map is used for, like how the artist originally intended. So you can see that here, and then when you increase it even more, you get like little finer details. And this is a huge part of realism and things like that in movies and computer graphics and stuff like that. And lastly, we'll show one more. So here's a nice moon scene, or planet, or whatever you want to call it. And so somebody created a terrain. So this is what I was talking about before. There's environments, but environment is just like another mesh. So you can take a look at it here. You can see little triangles. And now I'm going to decrease, or sorry, so now I basically reduce the tessellation, the fine level of detail. So so basically you can generate dynamic scenes, but the scenes are only as good as the amount of detail in the of the base mesh. So what you do is when you increase the tessellation, you can get finer details and things like that. And that's why it's like kind of like a big deal as far as like game and graphics programming goes, and even movies and visualization. So it's like right now, if this wasn't tessellated as much as it right now, there's only a certain amount of tessellation there, and that's why you're getting these kind of like, it kind of doesn't look really that great. But if let's say this mesh was even smoother, then those ridges and so on and so forth would make it look like very like more real, like something like this. I know it's tough, but anyway, so you can basically when you use this kind of technology, you can create all kinds of different scenes dynamically, and it depends on the artistic design and point of view, like what they want to design. Anyway, I just wanted to show that because that goes to the importance of tessellation, and like that was a huge breakthrough about 10 years ago that was made publicly available for programmers. Before then, it was you had to do it yourself. Like you had to basically make that algorithm, which I've tried doing and have been somewhat successful. But so you have that algorithm. You basically you either got to compute it manually on the CPU, which takes some cycles, and that's a compute intensive thing, let me tell you. So that was a huge thing. Okay. Okay. So and so the next point here is, so here's the graphics pipeline, and then what's happening is to the next point is, so now you have your CPU code. What is the CPU code doing? So here's your GPU memory right here. I'm just showing it right here, the GPU processor memory. Here's the memory. The CPU code is basically taking that data, the triangles and other things, as well as like functionality, which I'll discuss in a second, so it's taking that code and it's doing something with the GPU. So those programming APIs, you pass in the data and it's storing that data on the GPU. It's saying, hey, GPU, I'm about to draw with you, and I want you to store a specific amount of information for a specific purpose. And that's what programming APIs do, is to differentiate all those kind of purposes and functionality. And then the other CPU code does is it triggers the draw call. So it says, basically it tells it what to draw, when to draw, and how much to draw, and so on and so forth. So that's what's going on here. So you have the CPU code triggering calls, we call them calls, and storing data on the GPU. So here's the next section of programming overview. And this is just a quick information thing. So you have object-oriented class design. You have objects and classes to create, load, or manipulate 2D or 3D geometries. This goes a little bit step away from GPU programming, and this goes back to just a C++ programming. So in C++ programming, you can create objects, you can create classes, you can you write functions, you create code that does something, and so on and so forth. And so creating, but for computer graphics programming, the purpose of that code is to manipulate and interact with mesh data or mesh information to do something with it, either compute it or to like to display it on screen, so on and so forth. So the end result of all that is going to be a predetermined or undetermined number of frames per second, or FPS, that consists of a sequence of images displayed on screen or saved to a file. It can also consist of a single frame or image saved to a file. So this is the other reason why GPUs are so important, is because they're not just rendering that image on screen once. They're doing that 60 and above, hopefully 60 frames per second, or any number of frames per second. There's a limit, but basically they're doing that successively at a steady rate for a smooth result to display something on screen. So it's working a lot. And so again, okay, so and that's the gist of that. And that's again a whole other section that we could talk about, but that's the basic gist of it. So you have data. It's organized by the programmer to be to visually be appealing or make sense to its audience or end user, and that's what the programming APIs do. And again, it's up to the programmer to organize all that data information, work with the GPU, and get it displayed on screen either as a single image or frame, or as a continuously running 60 plus frames per second. So that brings me back to shaders. So like I said before, it's a C language technology. It runs exclusively on the GPU. And there's different kinds of shaders. They're all structured the same, but they all have a different purpose. One's called a vertex shader, one's called a pixel shader, one's a geometry shader, one's a tessellation shader, one's a compute shader. Vertex shaders work with those triangle data I was telling you before. They're called vertices. The pixel shader works with the working with the color information and some kind of effects and so on and so forth after all that positional data is computed. A geometry shader is optional. So you don't have to use a geometry shader. What it does is, let's say you pass in some data, and you don't even have to use the tessellation shader. That's another one. These two are optional. But what it does is, for the geometry shader, you pass in the data, and it can generate, depending on what code you write, it can generate additional vertices, like some other kind of like blocks or cubes on screen that stem from the original set of data. Or it could create another section of an addition to the original data, so on and so forth. That's why it's called a geometry shader, because it generates new geometry. A compute shader is, remember I mentioned before, GPU code. and computing, that's one of the use cases. So compute shader is like a number cruncher, or it's just like a CPU program, but it runs on the GPU. So it's like you could write like an algorithm or a function that computes something like a Bezier curve, or like a solver. They're called solvers. That you can create a solver that basically takes a bunch of data in and does some kind of computation on it, and then it outputs some other data that doesn't have to be displayed on screen. You can just pass that in back to the CPU. And the reason why all this is significant, why have all this stuff, why is it like even a separate section, is because so the GPU has thousands of cores and it's utilizing parallel methodologies. So the structure of the compiled code is optimized to utilize all those thousands of cores. And so the things have to be written a certain way. There is one caveat. So basically in parallel compute and shaders and so on and so forth, remember I showed you before there was a single point that made up the triangle. Well, believe it or not, when you pass it into it, when that single point is passed into the shader, and then the shader is computing on that single point, every single one of those points are independently computed as far as the shader is concerned. Each mathematical computation is only computed on a single vertex. That's why they're called vertex shaders. And not all the data has access to other parts of the data. That's why it's a little bit different than CPU. And there's a lot of challenges there as far as like programmers go, and headaches and all kinds of weird things. But so it's a little bit different that not all the data available is available to work on. As far as like, let's say you pass in an image, you would only in a pixel code, in pixel shader code, you would only have access to one pixel out of the thousands in that image. And you could only do some kind of computation on just that one pixel. Now, there's ways of accessing the other data, but you get the idea. And so like I was saying, so because each vertex or pixel is computed separately in parallel. So here we look at the CPU and the GPU. So the CPU has a few cores, and it's designed and it's optimized for serial tasks, while the GPU has thousands of cores and it's optimized for parallel tasks. So there's a big difference there, and lots of challenges. Okay, now we're on. Okay, and actually, really quick, I'm going to show you something really just very fast about shaders. Here. Okay, so let's take a look at a shader code really quick and see what I was talking about. So here is a shader. This is usually you have a separate vertex shader or a pixel shader, but you can, if you want, you can combine it in one file. This is called a pass-through shader. It's not doing any computation on it, but you could. So here is like a struct is defined. For those that know what a C++ struct is, it's just it's like a class or a structure that holds other data types inside. So, and then see where it says VS main here. This is a vertex shader. What it's doing is it's going to say I'm going to pass a PS input struct out after I'm done computing. And so this is going to be computed on the GPU. And if you look at, so here's a vertex shader. It has the same kind of structure as a C++ function. You pass in information here. That's positional information. That's the color information. We don't do anything usually on the color information in the vertex shader. You can, because that information is going to be passed to the output into the pixel shader or to the next shader in the graphics pipeline. So it depends on what you're implementing, like whether it's a tessellation shader, geometry shader, what's next in the pipeline. The pixel shader is usually the last one in. So right now we're not using any of that. We're just using the vertex shader and the pixel shader. So we're going to pass in the position information, the color information into the pixel shader. And right now we're not doing any kind of changes to the color information, and we're just passing it back, and it's just going to be displayed on screen. Here's what a compute shader looks like. This is just like a small program that is written like that would be written on a like on a CPU, but it's going to be run on the GPU. And so here you have buffers. So what a buffer is basically a piece of memory, like a specific allocated amount of memory on the GPU. So that's what the programming API did before, is say, hey, I want to create I want so much access to the GPU's memory, so on and so forth, and but it's all very strictly typed. So in the shader, the compute shader, it's saying we have buffer 0, buffer 1, and we're going to have a buffer out. So this is a read-write structured buffer, and again, all these codes are in DirectX. By the way, I forgot to mention that earlier. There's different ways, like it's very similar in OpenGL and Vulkan, but right now we're looking at DirectX code, and so it has its own kind of syntax, like RW structured buffer, but on GLSL or Vulkan, it would have something similar. Because the GPU is standard across, like the GPU remains the same, and how you access it, either using OpenGL, Vulkan, DirectX, or what have you, they're all going to be pretty much the same. So anyway, so if you look at some compute shader here, it's going to do some kind of computation. Here you're specifying the number of threads, like you can spawn threads on the GPU as well as the CPU, and then it's going to output that data into the right here, the buffer out, and that's the way you can access that data from the CPU, because again, it's not going to be displayed on screen. It's a compute shader. That's going to be the way you access this the data once it's all computed. Like, so basically, you pass in data, the GPU does its computation. The CPU says, "Oh, you're done your computation." Yeah. So how do I access that data that was just computed? You know, that's the whole point, right? So it's saying, well, I'm going to use a read-write structured buffer, and you have access to that. And here's the read-write buffer, and you can take a look at the data, and that's how that's done. All right. Okay, and here's a camera and model view projection matrix. Okay, something called a frustum. Again, I was saying before that the user or the programmer makes the scene, so it has to be like it's all mathematically defined. So even this data right here, this is a virtual camera, is what they call it, and it has a specific point of view, just like a regular camera does. So if you look at a real camera or a video camera, it only has access to a specific part of the scene. Well, and in computer graphics, you have a camera, but it is not automatic. It's like Nikon didn't make it, you know, or whatever. It's like you have to define it mathematically, saying, hey, this is how the camera is going to work. And so that's what's showing here. And you have a light, and you know, so on and so forth. But so the frustum, or the view frustum, as it's called, is it's a construct that basically says, when I have my scene, when I have my data in the object, when I take a picture of it or display it on screen, this is a point of view and the amount of data that's going to go in the final image. And so this is what that looks like. It's in matrix math. So you have a projection, view, and model, and this is all like, so here it's showing GL rotate, blah blah blah, etc. And so you could rotate that camera a specific like angle, let's say 30 degrees to the right, and some of this data would change. But that's how that's being computed in the CPU. It's not automatic. It's not automatic at all. So it's like, however, programming APIs are a programmer's friend. A lot of this functionality is made available in libraries and so on and so forth. So then users and artists and so on and so forth can just concentrate on, you know, what the scene looks like, et cetera, et cetera. Last thing I'm going to discuss on the first section is lighting. So there's different types of lighting. Again, lighting is just a virtual construct. There's no actual physical light there. You have to mathematically reproduce the light or the effect that you want. And it can be very daunting to get the right effect. So there's 4 different kinds of lighting that they show. One is ambient. Ambient lighting is like fine little details of reflective lighting that you normally wouldn't see, but it comes from reflections, this, that. Ambient lighting is a way of simulating that. Then you have diffuse lighting. That's like the primary color lighting, like the primary amount of light that's coming in from a light. And you can have 1 to n number of lights in a scene at different positions with different intensities and so on and so forth, all contributing to the final picture. just like in real life with photography or videos. Like I'm sure you've tried, people have tried low-level lighting, high-level lighting, reflecting, all that kind of stuff, different situations. So this is in computer graphics. This is how you simulate all that kind of stuff. And these are different nomenclatures for as far as, like what different things are called. So then you have specular lighting. That's where the highlights. And then when you combine these three, here's the final result. Again, this is all done in code. Okay, so this comes down to our first Q&A. I think that took more time than I thought, but that's okay. And then I guess we started a little bit late. That's fine. But anyway, so I just want to make a quick note before the Q&A is in computer graphics courses, traditionally in higher education, it focuses on the math calculations, the algorithms, and optimizations of rasterization, ray tracing, and linear algebra speedups, as well as computer science data structures and algorithms. So all the mathematics behind the things I was talking about, that traditionally has been computer graphics. So that's why I created this thing as far this presentation as far as computer graphics programming, which just kind of emerged and is very important in the last 15 years. Before that, traditionally, it was mostly just algorithms and calculations and wasn't really focused on code. It was more on just techniques, how to make things faster and so on and so forth. Because the hardware at the time wasn't as good as it is now. So that in order to get even some kind of things working, they had to concentrate on those kind of things. So it's still a part of computer graphics programming. Like there's people in computer graphics programming that focus just on this kind of stuff, like computer graphics, as well as some programming. Whereas what I'm concentrating on is mostly just programming, application development, and so on and so forth. So a little bit different. It's just a changing field. And any questions? Let's oh, and really quick before the question, sorry. There's something there called rasterization. Rasterization is what takes the triangle data and it flattens it. It basically like when you not just flattens it, but it does some other stuff too. But it basically takes the little triangle data, and once there's a rasterizer built into DirectX or the programming API and so on and so forth, that turns it into like some kind of visual image. It's a whole really big section of computer graphics, and you can look up that key term and hopefully you learn more about it if you're interested. Okay, so sorry, any questions?
Oh, I think there's a question already in the meeting chat.
All right, let's take a look. Yes, it does. Okay, so the question was, an integrated GPU that we find in Intel and Ryzen processors, does it follow the same architecture you described as far as accessing the GPU, or does it use the CPU serial approach? So the question is, so the answer is yes. What it does is, on the we talked about that display subsystem before. To the end user, that integrated GPU just looks like another GPU, and it could be less powerful or more powerful based on its the chipset and so on and so forth. And it does have it in addition, it has advantages as far as like it has direct access to the CPU's memory cache and so on and so forth. So that's used a lot of mobile processing where you get a little bit of extra speed up. Good question.
I have some questions, but I don't want to monopolize because I've got about 9 questions. So I'll just wait to see if there's anybody else that has questions. Okay, there's another question in the chat.
Yeah. Okay. So is functional programming also used? So okay. So believe it or not, I have a little because I've been in object-oriented mode for like 20 years. I'm a little bit iffy on functional programming as far as its a direct a definition, but don't worry about it. Basically, so okay, so the C++ and object-oriented programming is like the preferred way of programming. So once you have your low-level APIs, which can be like written in assembly or driver level code and so on and so forth, there's a lot of different language variations available as far as accessing or making function calls to the GPU. I hope that answers your question. And there's like what we're looking at right now is the low-level API. So that's right from the manufacturer, like Microsoft, Kronos Group, so on and so forth. They work together with like different companies, and they create a low-level API. That's like the most simplified version of being like, it's not even simplified, but the most lowest level of API next to the driver or next to the to access the GPU. There are tons of other software libraries built on top of that that are available. That could be open source or proprietary or whatever, that make it much easier to program. But for the purposes of this webinar, we're looking at low-level APIs, and it's like the most extensible thing as far as being flexible.
Now, one of my questions, what was that website that you showed that showed the arrows and the figures that you built up from the arrows and the points and the lines? I couldn't read the URL that well.
So just where the showing the primitives, like the lines, the triangle
Exactly.
strips. Okay, so
Exactly.
that was just Microsoft's DirectX documentation. That was actually being shown on, so the primitive is on DirectX 9. So there's different versions of DirectX, but that's where that particular page was.
Could you just put the URL into the chat? Oh, somebody did, I guess. Got it. Thank you.
Thanks.
Another question I have, and I'll stop if I see other questions coming in, I'll stop. Um, how leveraged is this? And what I mean by that is, let's say that you have all the hardware available, you have all the primitives, all the languages, all the API, everything exists for you, okay? And you want to build up, when you were showing those lunar scenes with the galaxies in the background,
Yeah.
and you changed the tessellation, you swept the tessellation parameter and you made it more or less tessellated. Okay, so that's fine. But let's say you started where you got all the hardware and software available, all the utilities available, but you want to build up that lunar scene to begin with, and then and then sweep the tessellation. How much user effort, human effort, is involved in just making the lunar scene itself?
So that, just to make that scene itself, is lots of okay, so wait, so are you talking about like you don't want the scene tessellated and things like that, or you do?
I just want to know how much additional programming or whatever other effort that humans have to do to make a lunar scene to begin with before you start tessellating it further.
Okay, so that in itself is a lot of work, but
Hmm.
so, and the reason why it's a lot of work is because it's we're talking about object-oriented code and reusable objects. So the general, if it's done properly, when you create the lunar scene, not only will you have a lunar scene, but you'll have the building blocks for any additional kind of scene that you want to make. So there's like prime zero, like in any kind of math equation. Like, so the initial state of creating your first scene, there's a huge overhead. So, but once you have that first scene, you could like, you already did a lot of work there. You can reuse that work into creating additional scenes. So if it's, so the question is like, so it does take a lot of work to do it properly. If you just want to create a simple scene where it's like you have a mesh, like a rounded mesh, with a that you're going to be able to tessellate later, and you have a background that shows the space scene and so on and so forth, that's not so much work, but it's still a good amount of work. And in addition, to make it interactive, which is a whole other set of things we won't cover. Interactive means like you put some input into it and it changes state. That takes an additional kind of work as far as developing like a system for walking around, uh, uh, rotating your view, and all those kind of things. So it gets pretty complicated.
Right. Okay. I'm going to skip over some of my other questions, but let me ask you this one, and then I'm going to back off because I want to make sure other people have a chance to ask questions. Um, what are the various types of applications that this technology can be used for. Above and beyond, as valuable as it is itself to have entertainment, um, entertainment applications, movies, etc., art, whatever. What are other types of applications that this can be used for?
Okay, so I'm going to cover some advanced usage stuff in a near the end of one of the slides, but
Okay.
basically, so you have any industry that like involves visualization, like simulation. It's used a lot in simulation, engineering work, modeling, not just modeling for entertainment, but modeling for like architecture, modeling for like landscapes, planning. Lots of that kind of stuff. Um, uh, like I said before, video processing. It's GPUs are so video processing for the GPU. That's even a separate a separate group of APIs. So everything we talked about up to the DirectX calls, that would remain the same, and then you have like another set of programming APIs or libraries that you would use to do video kind of work. Like, so it's like video and image processing is really big as far as like like um, like image segmentation of images, like capturing stuff from a camera, and then like machine learning, all those kind of things. So it's like lots of use cases, but I'm going to cover some of the advanced stuff in additional slides.
Okay, I'll hold off on my other questions. If anybody else has any questions, go ahead. It's 8:08 right now. If anybody has any quick questions, go ahead. Otherwise, we'll wait a second, and then if nobody else has any questions, then why don't you go ahead, then Nav.
Yeah. Okay. And then so Sharif has one last question about ray tracing. So basically, ray tracing is a completely different way of getting that final image on the screen. So when you have what we were looking at earlier, that's called rasterization, where it's like the image is fed in, and the lighting is calculated dynamically as per the shader. Not the lighting, sorry, the final way that the mesh or the 3D model or 2D thing or whatever, the final pixel on the screen is determined by the shader. And it's very it's as precise as it can be. Ray tracing is a way of simulating light without knowing what the without it's just a different way of doing it. Basically, the way what it does is you can you pass in what are called rays, and then the rays bounce around the screen, and you have to compute whenever they intersect an object. So the way rasterization works is saying, hey, here's an object, its color is red, and it's this amount red, and that's it. And then you can like kind of pass in other information or data that say, well, it's kind of like this color red because there's something near it. But with the way ray tracing works is it's going to say it's red, but then there's like, let's say there's 20 other objects around it. Those rays are going to bounce around the screen, and they're all going to be computed on those different objects. And then the information is going to accumulate, and then that final piece of data is going to go right to that where that pixel is, or where that object is supposed to be in that pixel. And it's saying, well, after it's simulated all the light bounces, what's the final color on that image, right? So it's so one is a simulation approach, one is more of a finite math approach. All right, and I guess we'll get on to the next section then.
Yeah, thank you.
And a great question. And we're going to okay, so really quick on ray tracing, we're going to talk about that at the end. We're not going to really talk about it, but there's a new kind of hardware out called RTX, and it basically allows ray tracing on the GPU, like not automatically, but it's kind of did the same thing what tessellation did. What I showed you, the tessellation shader does. It allows ray tracing to be done more readily and quickly and more efficiently, basically. Programming wise and computationally on the GPU. So there have been huge changes. Ray tracing is a huge topic in computer graphics, and I suggest everyone look it up. And it's very interesting. Okay, so I will get back to the slides here. And okay, so really quick, a program requirements map. What is this? So this is, what do you need to be a computer graphics programmer and like to take it seriously, or so on and so forth. This doesn't really pertain to you if you just want to like do some computer graphics programming. But if you want to be in the field, you want to do a career change or whatever, you kind of have to have a good fundamentals in these kind of topics. And I'll explain why. So you have a basic foundation of programming like C++ or Java or whatever. You know about object-oriented programming. You need to be good at debugging, computer science, and or software engineering. And you have to have a very strong interest in computational geometry or mathematics. And why? Because it's so diverse and it's growing so much. Like you have program managers, you have people wanting to use it for different things, so on and so forth. And so it's very complex, and there's a lot of subdisciplines involved. Like you work with artists, work with engineers, work with scientists. So you kind of have to have a strong foundation in order to do anything. And there's like I was explaining before, there's a lot of complexity just to create a simple program. And then simple programs can be user interface design stuff, interactive desktop applications. And then so like all those like user interfaces, interactive desktop applications, and games. So like they're very complicated. Like a game is highly complicated. A desktop app is highly complicated. User interface, highly complicated. As far as the computer graphics are concerned, lots of things going on there. But I remember before I said my degree was in HCI, human computer interaction. This is what we study, and I'm in the computer science stream of that. Is like we have to work a lot to make things, just like in any field in engineering, is like we have to simplify that enough so that the end users are able to interact with the program, and basically in all types of end users. So it could be like children of all ages, adults of all ages, adults of different educational backgrounds, so on and so forth. So part of the challenge is once you have this complicated thing, one thing is just get it working. The next step is how do you simplify that to make it user friendly. And that's like the field of HCI that I was talking about, like where we study user friendliness and how to make things better and all that kind of stuff. And so that's why a lot of stuff's going on. And another reason why is there's an abundance of technologies to choose from, and there's stuff from industry, there's stuff from open source communities, and you have to be able to decide and say, oh, I'm going to use this for that, I'm going to use this for that, this is better for this situation. So lots of engineering, lots of software engineering, lots of computer science stuff, performance metrics, all kinds of things, and it's very much decision based. And it can be very, very tough sometimes. You have to be really dedicated. And it really took me 8 years to get to a near expert level. So I'm kind of gotten to that, and where I'm trying to be one of the best computer graphics programmers in the world. And but it took me 8 years just from that, from an enterprise developer programming background. Lehigh helped a lot as far as being able to make that switch quickly and effectively. Usually it would probably take you more than 8 years. I gained a lot of fundamentals from the computer science courses at Lehigh. There's big rewards. So gain skills useful in any programming industry. You have your cool factor going on, gaming, entertainment, and science. Huge performance gain in programming, like because it's so hard, when you do it and you keep at it, at the end of the day, you will be an exceptional programmer, basically. And then the other thing is you'll be a very important part of a team. Like different team members have different roles. Because it's so difficult, you're useful to a team. And also the other cool thing is graphics, media, and multimedia are like pro future, right? So like everything's going visualization, video, interactivity, so on and so forth. So it's an upward trend and very interesting field to be in. Okay, so we're going to take a quick look at an actual program which I created just for this for this webinar. It's a simple multi-threaded desktop application. Multi-threading is super important for computer graphics programming. So then once that's set up, we add vertices and texture. We actually add the data to the multi-threading, and that gives us our final image on screen. So I'll go through this the vertex where it says vertex meshes after. Really quick, let's take a look. And okay, so here is a Windows 32 desktop application. This is what it looks like. Everyone's used one of those where it's an application on Windows that has a window. So if everyone can see this, here is, for those that don't know what multi-threading is, or threading, this is a specific function that's going to be created and run in a separate thread from the main application. So when the application starts up, it has its own thread, which is a process in memory, and then it's going to spin off another thread, which is just going to do the drawing. Now, this is very important in computer graphics programming. Like I was saying, like optimize efficiency, extensibility. Code becomes a lot, so it's keeping everything nice and neat, and so on and so forth. It's really important. So really quick, so I have here a graphics drawer.
Real quick question on another thread within the same processor or spun off to a different processor?
Same processor.
Okay, thank you.
Yeah, no worries. And but the end goal, so this is a simple app. The end goal is to get some drawing done on the GPU. So there's three important things going on here. One is, so we have a graphics draw. This is what's going to do the actual drawing. Here's this, it's a separate class I created. And we're going to pass in an hwind. Hwind, or I call them hwinds, is a handle to a window that we're going to create. We're going to create the window from scratch. Or the window is created from scratch. It's actually, this is like a template wizard code just to start. So the template wizard code lets you create the window. Once the window is created, you get a handle to it. They're called handles. So basically that handle is passed into the programming API from Microsoft called DirectX. And using that, we're going to have a displayable surface to do some drawing on. So here is the graphics drawer class that I created. If you scroll down here, this was done for me, but I changed it a little bit. So you have graphics window is equal to create window, and then so we're creating a window. Like that's like I was saying before, everyone's seen that. Like everyone's used that. It's like a window where something is going on there. And so what we do is, this is a separate function here, but once that window is created, we're passing that into the to this class that I was just showing you before. So in that class, okay, before I do that, let me just finish up with the multi-threading. So what's going to happen here is, here we have a very important concept with multi-threading is you have an exit event when that thread is, once the thread is created, eventually it'll exit. This is important for safety reasons and preventing memory leaks. So you have your exit event, and then here you have your create thread. So this is going to create that separate thread, and it's going to do some drawing in that thread. And so all user interface programming and computer graphics programming uses some kind of pattern like this, or framework, where you have the main application thread and you have a separate thread for drawing. It doesn't have to be, but in order to get any kind of performance speed up, or like the proper way of doing things, is you create it in a separate thread. So once you create, we create the thread, the program is going to run. It's going to say, while the app hasn't exited, or if we explicitly tell it to stop rendering, rendering means actually drawing to the screen. If the graphics, if all the graphics resources are available like we told it to be, which we're going to cover in a second, if it's ready to draw. Now, I didn't really use this, but this is important for graphics drawing. This is for like animation and or state changes. You're going to update the graphics class with timer information. So timer information is like a clock, like, so the everything is running on a clock. Like you can just like when you press play on a video, you can forward it, you can rewind it, and so you have to basically for advanced programming, you have to create an animation or whatever that accepts input in as from time, and based on that time value, it changes its state, whether it's a rotation, whether it changes color, whatever. So that's up to the programmer to decide when they write the program. And then once all that data is transformed based on the input here, and there can be other data as well. Right now we're just passing in a time, and that's usually the default or the de facto for animation and graphics drawing. And you can also pass in input data, which is like somebody clicked a button, somebody moved the character forward. You know, it's all kinds of data you're going to pass into to be drawn on screen, because every single frame, not every single second even, every time that frame is redrawn 60 frames a second, that character or object on screen could be changing state. State means it could be rotating, it could be like animating, it could be producing some kind of effect. So there's all kinds of things going on there. But for this intents and purposes, this is a simple drawing app. This isn't really used, but we have so the draw command basically tells the program that hey GPU, draw this, and then we're going to display it on the screen. And then this is a fake timer here where it's just being incremented 0.001 points, or a decimal point per second, you know, and that's passed in at like through the loop, because this loop is just running at will until the program stops. Once we tell the program to exit, it's going to set the exit event, and the app will be exiting. But let's say we didn't set that exit event, there would be a whole bunch of resources. Here we go. See, so right now it's saying wait for the single object. So if let's say we told the program to exit and this was never called, it would wait here until infinity. But because we want to wait until this thread to exit, we want to delete the object afterwards. And basically that creates safety and prevents memory leaks, like I mentioned. Just something to be aware of. So now we look at so this is where a lot of things are happening. I'm just going to go through this quickly. Basically, we passed in the window. Here, this is a programming API information from DirectX. So this is how DirectX does it. OpenGL will do it a different way. Vulkan will do it a different way. So what's happening here is saying, hey, I want a DXGI factory. And that factory is going to let me say, hey, I want to know how many GPUs are in my system. And so once I have that, I put this command in, and this is like different APIs available from the different programming calls available from the GPU. So I mean from DirectX. So the DirectX system is saying, I have this many GPUs in the system. Here's a list of them. So I got that list, and then it's then right here, this is where I'm creating a device. It's called a device and swap chain for my application. So right now, while the computer is running, each application that's running on the computer has its own separate device for drawing. So right now I'm creating mine for what I'm going to draw. And so it says, hey, I want to use the first GPU I have in the list, and I'm using DirectX 11. Here he says D3D11. And I want to create a device to use for drawing. Basically, this is giving me access to my GPU resources. So this is saying I need some resources on the GPU. Mind you, for systems like, for example, that have just one GPU, there's only one GPU, but there's a lot of applications and programs using that. So the GPU has to keep track of all that. And that's basically what's going on here. It's saying, hey, I have this program I'm creating. I need a GPU just for that. And this is what that does. Then we have, so right here, I have two sets of data. I have my triangle vertices and I have my quad vertices. One's a triangle, one's a quad, like a simple plane on the screen. Then we have some, and this is the triangle data I was telling you before. So it's composed of just the triangle is composed of 3 points. The simple plane is the simple rectangle on screen, which is a 3D plane, but it's a flat. See right here, it says there's no z coordinate. Same thing with the triangle. It is a 3-dimensional object, but it's going to be displayed flat because there's no z coordinate. There's basically 2 sets of meshes that we are going to be drawing on screen. Actually, we're only going to be drawing one, but you can choose one or the other. So here's where the other stuff goes on. This is create a render target view and get buffer from the swap chain. The swap chain, this is very important. This is why I want to mention this. Graphics programming. Whether it's OpenGL, DirectX, whatever, this is going to give me a piece of video memory on the GPU that says this is where I'm drawing to on the GPU. So when the GPU does all its computation, it has to draw to a specific, like we see it as a rectangle, like whatever we're seeing on screen. But what it is all it is in video memory, it's a specific portion of that memory that's been allocated for our application's use. So right, and you can create multiple of those. You could create 1,000 surfaces on the GPU and never use them, or use them all and never display them to the screen. But for all intents and purposes, see the swap chains portion of memory that we created when we created the device, that's giving us what we call the back buffer. That's going to be the final image. That's going to be the final piece of video memory that's going to store all the pixel data to display the final image. Then we create something called a render target view, and that's just Microsoft terminology and stuff like that. Basically, that's like the portion of the memory that we just talked about that we want to see displayed, and that's enough. That's as much as I'm going to say about that. Then we set different settings on the GPU, saying, "Hey GPU, we're getting ready to draw on you. Here's for this particular frame, I want you to do this, this, and this." So we're setting the shader. This is the same shader I showed you before. It's just a simple pass-through shader, the vertex and the pixel shader. And so anyway, so when the draw call is called, right now we're in the draw function. That was remember in the oh sorry, we're not in the draw function yet. Right now, this is getting set up to draw. This is when the graphics device is first initialized. We pass in the H-wind, or the handle to the window. This is basically setting up the GPU to draw with the window. So we say, hey, this is the vertex shader we're going to use. This is the pixel shader we're going to use. Why is this? And here's just something else very important. Here's the vertex buffer we're going to use. I skipped that for a second. Let me get back to that really quick. That quad and triangle data that we had, that has to be sent to the GPU. Where does the GPU store that? It stores it in memory. Those are called buffers, GPU buffers. And right now we're creating a vertex buffer, it's called. And that's basically allocating space on the GPU, saying, hey, this is where we want that data to be stored on the GPU. So it creates the buffer with some specific number of data. Right now I'm doing this dynamically where I'm passing in the triangle vertices. So these are triangle vertices being passed in. I can change that if I want to quad and the number of vertices to 4 instead of 3. And it would display a quad. But for now, we're displaying triangle. And but anyway, so then you have to tell everything to the GPU. It doesn't do it automatically. So it's like you pass in, here's some set of data, here's the attribute information, like that it needs, like the number of vertices, like what kind of data is it. So here's another thing we didn't cover yet, but I will show you. So this is a struct. This is a byte-aligned struct, which makes it a little bit optimized and run a little bit faster on the GPU. Basically, we're passing in a float of 4 as positional data and a float of 4 of color data. And then I showed you that before with the quad and the triangle. So you have to also tell it, like, this is what's going to be running. This is the kind of data that's going to be running on the GPU. Whether it's a triangle or a quad, the GPU has no idea. That's like that's a human definition, but we can tell it that, hey, it's going to be this size of data, a position and a color, and there's going to be 4 or 3 of them. So it'd be this amount of byte data times 3 or times 4 or times whatever the size of the mesh is. So that's what we're doing here, and then we're telling it, hey, we want to use triangle strips. Remember we covered that in the beginning with the primitives. This actually should be 11. But anyway, so we got told that we want to use drawing lines. So when you pass in the vertex data, whether it's a quad or a plane, it could draw just like using lines. It wouldn't draw a triangle strip. Then finally, we set the target. And what I wanted to say previously before I got to the vertex buffer was you could actually create thousands or hundreds or whatever of different shaders and then allocate them in memory. And then you can switch them every second, every state change. Like, so you could have a blue shader, you could have a green shader. And basically, like, so let's say the mouse or somebody clicked on an object, right? And you want to change the color and you want to change like how it works, like the calculation and so on and so forth. You could set the shader. So at runtime. So basically, that's what the programming code does, is that you create a shader, it does some kind of computation, it's like a mini program, and then for different objects on the screen, or even the same object with different state changes, you can set the shader, and that's what this function here does. It say, hey GPU, I want to use this shader for this second of time, or this frame of time even. And so that's where you have a vertex shader here and pixel shader, and you can change the different shaders. And I know it's really complicated. I apologize if it's a little bit much, but that's the way it is, and that's a simple program. And let me show you the last part for when it draws. Once all that is done, you do that once, and I'm going to talk about that for a brief second. Once that's done, you allocate all your resources, you get the GPU ready to draw and ready to work with. Let's go back to the main program. We're only doing that once in the beginning before any kind of loop happens. That was right here. You do that at the beginning of the program during an initialization function or part of code or whatever. Once it starts the loop and the thread is created, is ready to draw, like everything worked fine, where there were no programming errors with the GPU, and the GPU is ready to roll. Then you call these things 60 frames per second or 1,000 frames per, or whatever you can do, or whatever. You can just let it run. But you know, like to get some kind of drawing done on the screen. So inside this loop, we're not going to be reallocating all those resources and all those things. All we're doing is just drawing inside that loop. So here's this draw call. What's that doing here? So here, all it's doing is, because this is going to be run like 60 times a second, literally, and it's going to be refreshed on the screen 60 frames a second. So what this is doing is going to it's going to clear my screen to a certain color that I predetermined here. Then, because this is a little bit different if you have multiple meshes on screen, but for all intents and purposes, we set we told the device context before over here that, hey, these are the vertices that we want drawn. We're not going to change them. We could change them, but we're not going to change them because they're done in this part of code. But those are the vertices that are currently ready to draw on the screen. So that's what this does right here. This actually triggers the GPU to go through that graphics pipeline from start to finish, in our case from vertex shader to pixel shader, as well as the output stage. And then on that piece of memory that's in the GPU that we allocated, that back buffer, it's going to draw something. Now, because it's being drawn so fast, 60 frames per second, we then have to tell the swap chain, we want so there was, what the user is seeing on the screen is one thing, that was last frame. We want to present the new frame to the screen. And that's how it works. And that's called, and in this case, it's presenting the back buffer to the screen that the user sees. Until you do this call, all it does is draw on that surface, that part of memory in the GPU, but the user never sees it. Once you present it, it discards the old scene, whatever you were seeing on the screen, and it presents the new scene. And we're going to run this code. And hopefully everyone can see that. We right now we have a clear, like, so basically on that piece of memory, there was that color was, that piece of memory was cleared to a certain color. That's what that one function call does. And I predetermined that color, and I said, hey, I want the background to be, or I want all part of that back buffer to be this color. Then the pixel shader, I'm sorry, the graphics pipeline said, hey, I'm going to take that color information that we passed in and that vertice information, and I'm going to, just using 1, 2, 3 points that are all connected, and it checks to see if those points are connected or not in a triangle strip mode. The other part of that data was there was blue color information at this vertex. So right now all the GPU had was 1 point, 2 point, 3 point. And at that point here, the associated color was green. The other point that was associated with this point was blue. The other point here was a red. So what the rasterizer does, and it takes all that color, it takes those 3 points and it rasterizes it, and using an algorithm, and like I said, it's a huge part of computer graphics research, not computer graphics programming research, but what scientists have been working on for many like the last 20, 30 years, is that algorithm makes it look like there's a flat triangle on the screen. And that's what's taught to graphics programmers. Say, hey, if you want a shape or something that's like a triangle, you pass in 3 points, and the rasterizer will take the rest of it. Will take care of the rest of it. And really quick, I guess I'll just quick is, so if I change this to number of vertices 4 and quad vertices. So now we're passing in. So here's that data here. This is the point data. This is 1 point, 2 point, 3 point. But remember before I showed you the vertex color struct. So the way the GPU sees it is it sees it as point. Here's the color that's that point. And you could have other sets of data too that it might have to do with physics and all kinds of stuff. But for our intents and purpose, we're passing in a vertex and a color. So we have a point, color, point, color, point, color, point, color. And that's a set of data. And before we had a triangle, like it was only 3 points. But so now we have quad vertices, and everything's set up there. And if I click that, again, the graphics pipeline didn't change, or the program didn't change, but the data we passed in did change. So here's so what the rasterizer did is it took 4 points in, and the different positional data and color data, and then it created this object on the screen that is presented to the viewer. And that's how that works. And that's a very simple graphics application. No, done very, very well. Like that's like a nice, safely memory safe program. And all right, next slides. Okay, so here's a quick explanation of that really quick that we just saw. So you have different points. You also have something called indexing. Indexing is like an optimization. What it does is you pass in a whole bunch of points, and instead of the GPU going through each one of those individual points as they are, like you see on the left-hand side here, vertex mesh, it's interpreting the index instead. So what you do is separately, you say, I'm going to pass in an array of integers like 1, 5, 10, 12, 15, etc. And it's an ordered list in triangles that say, on the left-hand side here, you can see a set of vertices, and the set of vertices are in an array, and they're ordered. So this first phase is 0, 4, 5. I'm not going to go through this, but basically what the index list does is it gives it like it's called indexing. The indices tell the GPU which vertices to use to create a triangle. And what it does is, if you noticed, you can use this vertex. Let's say you pass in let's say there was 1 million of these points, of vertices you passed in, and it all contained a whole bunch of complex data. You could pass in, and this is another part of computer graphics programming that some people specialize in. It's not what I exactly do, but it's like something I've been doing, or that you should know how to do, and all that kind of stuff. But then you could have different index lists pass in, basically define what different objects look like, but using just one set of vertices. So basically, it's like a way of optimizing and saving space. Pretty important. It's a huge field. If someone wants to look it up, they should. And here's something else called texture coordinates. Once you have that base mesh and you're using color information, you don't have to use that color information. That's just what the pixel shader was doing. What you can also do is you can pass in a texture. So you create your 3D model. You have your UV map. That's what texture coordinates do. And the texture coordinates say at this point, we have a specific coordinate, a UV coordinate. At this point, there's another coordinate, and that maps to this. So when you take this flat UV map and this flat image, this image is going to, using this UV coordinates, is going to map to this 3D model. And that's what UV coordinates does. I know it's not the greatest explanation, but basically it's a pretty important part of graphics programming, but it's a completely separate topic as far as like intro to computer graphics programming is concerned. It's still a part of the introductory model, like basics foundations, but it's not, I don't think it's, we should go any further as far as this particular webinar is concerned. Okay, things to look out for. Things I was discussing before, object and class instantiation. Never, you know that draw function we saw before? Never create objects in that draw function because that function is going to be running like all the time. So it's like you want to be careful. Like, so what all that draw function was doing was triggering the GPU. Like that doesn't take up so much CPU time. That takes the minimum amount of CPU time possible. All it is like a simple call that says, "Hey GPU, do this. Hey GPU, do that." It's not creating. It's not telling GPU create new memory. It's not saying, "Hey CPU, create new memory. I want to store some objects. I want to do a copy thing." It doesn't do any of that kind of stuff. So you have to be careful when you're creating objects, as well as how many objects you're creating. And then you have to like look at things like caching of memory. Same thing like high performance computing, like same kind of principles. You have to be very aware of what you're creating, and you have to be able to map that whatever you're creating on CPU side, that you're creating an object, or let's say you were creating a million triangles or a million planes, or you're creating 5 characters or 20 game characters. You have to map that to GPU memory eventually. So you have to be able to keep track of everything. There's something else called batch processing of objects. So this is called instance drawings. This is like important part as well, but I'm not going to cover it today. It's called instancing. So instancing in computer graphics is, let's say I had that mesh, the triangle or the quad, and I wanted to draw 20 quads on the screen. So what instancing allows me to do, it's an API function from like DirectX or OpenGL, and it lets me create the mesh once and then says, hey, here's some extra data, which I pass to the GPU. And that's done a certain way using programming APIs. And I want to create that mesh once. It only uses 4 vertices, but the GPU is going to draw it 20 different places and automatically. And the reason why that's important is whenever you do a draw call, like I mentioned before, hey, I was telling the GPU draw once, right? Or do a draw call in the draw function as optimization. The thing is, let's say you had a million objects you wanted to draw on the screen. You only have to do that draw call once instead of calling it a million times, because on the CPU, that takes up a lot of time to call the same function a million times. So you have something called instancing where you can draw the same object a million times on the screen at different places. And there's a huge optimization there, big time saving. Spatial tree usage, that's an important data structure in computer science. Very huge in computer graphics and interactivity. I'm not going to cover the ins and outs, but you had to take my word for it. And basically, that's one of the reasons when you have lots of objects on screen and you want to be able to interact with them, like click them or put user input, like from a game controller and so on and so forth. Spatial trees are extremely important as far as being able to enable that interactivity, as well as keep your performance within guidelines as far as like processing speed, memory consumption, and so on and so forth. Primarily performance. So it's mainly a performance thing. And then also an important thing is you have to be a really great debugger, because frames per second, like, that thing is looping all the time, and it's like it's running like crazy amount of code all the time. If you have a memory leak, it can accumulate quickly opposed to days. Like when you have a memory leak in CPU code, it doesn't accrue that often. You might find the memory leak like five days later or something like that. But with computer graphics, because there's so much code, and if you have a memory leak, it could lead to like the program not crashing right away or something like that. How are we looking at on time?
It's 8:46.
Is everyone okay? It's just gonna be a few minutes longer, like 15.
Okay.
Is that okay?
Yeah, I guess so. I mean, people are free to stay or leave as they see fit.
Yeah, just like 15 minutes left. It's almost done. Okay, so basically, I'm going to show you some quick samples, like some advanced code, not advanced code. It's like they're also like code I showed you before with the moon scene and this and that, but it's going to be similar to what we just did, but a little bit awesomer. And okay, so here we go. So the first one I'm going to show you is it's called an island. It's a sample. These are samples from NVIDIA, by the way. Give me 1 second. Let me show you that on this thing. So here is a little bit more complex scene, and this is called the island demo. And is that coming through okay?
Yeah.
Okay. So this is the island demo, and the reason why I wanted to show this is so this is like a pretty basic like interactive scene where I'm traveling around and here's the island, but basically all it's being passed in is there's two quads, two planes like I showed you before, and they're being tessellated and they're having like there's different information being passed to the GPU. And so if I click wireframe here, oh my God, that's a lot of tessellation. So here's the basic of it. This is like what was passed in, like the vertex data, and then the when you,
And
the
was
different
and
part. Oh, go ahead.
was there a lot, don't forget what you were going to say, please, but was there a lot of effort, upfront effort, human effort involved in generating just this data?
Yeah, well, it's like that's what like there's some guy that works at NVIDIA. He works all day and he makes this happen. Like maybe it took him 6 months or something like that to do it properly. So like this particular piece of code is a sample code which other developers learned from. So there's another way of doing this where it wouldn't take 6 months, but the way they do it is that so people can learn from it, like the proper way of doing it and all that kind of stuff.
Okay, and so to continue, you were about to say what?
So what I was saying is, but even though this looks like a complex scene, the amount of data that's being passed to the GPU is very similar to what I showed you earlier. It was just in finer detail, like takes a little bit of planning and all that kind of stuff, saying I want the shape to be this way. Uh, the ocean, the way it's moving, that's being done using a clock, but then that clock information is being passed into the one of the shaders, and the shader is computing those waves, like the deformation of the mesh at each single vertex point. So even like when you tessellate, so here's the base mesh, or here's a simplified base mesh. This is what's passed in. Each one of those vertices are being calculated like one way or the other individually in that shader. So that's what that shader does is each one of those points, whether it's up or it's down, using some kind of predefined formula that the programmer put in. Now, here's the clever part. It's like, so it's being moved up and down to simulate an ocean. Now, the clever part is with tessellation is let's say, see, this is how it looks like when it's not tessellated. So if you did tessellate, this is just like the data as it is. It doesn't look that great. I mean, like what people would want. But when you tessellate it, you get so much finer detail. But that's being done automatically because the programmer wrote the code correctly. So that's like the important thing.
How much memory does something like this take?
I couldn't tell you, but not much. Like this is not a computer graphics. This is not an intensive application. Like if you look at right here on the up above, at least not anymore. Like right now, this is running at 850 frames per second, where like the expected thing is like 60 frames per second. So it's like this isn't taking up much memory at all.
Okay, and you were about to say something else before I interrupted you.
No worries. Okay, so this is using the DirectX pipeline way of doing things. Remember I showed you like there's a pixel shader, vertex shader, so on and so forth. There's also another way of doing things. Really quick, I just want to show that it's using the compute shader, like scientific engineering. It's a little bit different, but I just show you the example really quickly. And we're almost done. So this one is done on the compute shader, like using just like a program that like, so it's the amount of, oh, sorry, let me share that. It's not on screen yet. Oh, 1 second. There we go. So this demo is called Direct Compute Ocean because the majority of the computational data is being passed to the compute shader, which is being run in a different kind of way. Anyway, I just wanted to show that it's 1 second, and but there's
That's
different
beautiful.
ways of doing things. Sorry, go ahead.
You're about to say something?
No, I was going to say, so there's different ways of doing things. So it's like when you become a computer graphics programmer, at least in the modern sense, you have to be able to understand like there's different, like so for a video game, for example, let me give you 1 second. For a video game,
I was just going to say that's beautiful what you were displaying.
yeah, no, it's amazing. But for example, for a video game, people don't care about like the detail of the ocean. Like they don't want to see that it was like it was accurate, like it's exactly like an ocean scene, right? So a lot of people, they use the compute shader because it's they have a little bit more finite control of like of what kind of data they can enter in, and they get more precision. So with you get a more like realistically simulated ocean effect, basically. So there's different advantages to different things. I just thought I'd put that out there. Okay, I'm going to go through this really quick. Here's advanced applications and usage. You do game engine, game development, interactive applications, photo, video editing, digital content creation tools, like the tools developers use to make models. They're actually computer graphics applications themselves. Then you have cluster compute, GPU computing. This is a super advanced usage: simulation, engineering and science, finance, fintech, big data. Cluster compute is like cloud computing, but it's GPU cluster computing is like, so you have millions of GPUs working together that could like, but you still have to like, it's super, I mean, it's like cloud computing, but you're using GPUs instead. And then there's a lot of use cases there. Multi-device rendering. So that's when you combine like 5 or 6 GPUs on one machine. And once you have that one machine, you have like 20 of them, and you can create like a more visual effect. And they're largely done for like cloud-based gaming, VR, AR, interactive art shows at museums, and like those really cool huge displays that you see like Sony do an event or something like that. So they're powered like by like 100 devices or thousands of devices connected together. And then you can also do like advanced custom built user interfaces for applications or games. Like games themselves are an advanced use case. Okay, and really quick, I'm just going to show you this website developer. It's like how can someone do all this, right? Say, oh, that's crazy, like cluster compute, GPU computing, photo, video editing, multi-device rendering, right? Like that's insane, right? Who wants to do that? Well, the nice thing is there's also there's also libraries like for those kind of things. And so these are the kind of libraries. I just wanted to show this really quick. NVIDIA did a great job with in the last decade or two in developing these. And so one is like a GPU, so they call them GPU accelerated libraries. One is this like a basic linear algebra library. One's a fast Fourier transform library. One's a standard mathematical function library. One's a random number generator for those into cryptography and things like that. There's solver libraries for math nuts and people like me, which I haven't used yet, but I want to. Um, CU sparse. I'm not going to cover that right now. CU tensor. What's it called? There's a that I'm going to cover really quick on the last slide, and like what's a tensor, and then and some others, and then you have parallel algorithm libraries as well. So you have a lot of the work is done for you, but you still have to basically know what you're doing. And like it's a great community. It's good to be a part of them. Like working with them, and people try to help each other out a lot. So it's pretty great. And okay, so there was one video that I was going to show you, but I'm going to skip because I'm just going to show you this one at the end. So latest advances and future outlook. Now we have GPUs in cars. We have AI GPUs. This is the latest thing. This is like the last 2 years they just came out with this stuff. So you have something called DLSS and AI rendering. You have AI's models that are trained. They're used inside GPUs. You get huge performance gains, and you get like A lot of advanced a lot of new use cases are being figured out and stuff like that. Low latency cloud compute rendering, and so that's like GPU clusters being used to perform some task in tandem that because of like the internet's so fast and so on and so forth, you can do that. You can have like video games that run in the cloud that are now being played on a mobile phone. And another cool thing is you can have cloud bursting. Basically, it allows expensive hardware to be utilized at a scale at a fraction of a cost. That's what I was talking about before about GPU and cloud computing. So basically, it's like, let's say you're a small company but you do scientific engineering, but you don't want to pay $5 million for a bunch of like a data center where you need to process some data like 1 hour or 2 hours at a time a month. So what you can do is you can rent it, or the principles of cloud computing for those that are familiar, and you can say, hey, I'm going to use my own GPU devices and my own computing locally, but whenever I need to, the cloud's right there, and I need to, I'll pay $50 for an hour, and I'll have like 100 GPUs working at once. So that's like awesome. And so again, automotive AI and self-driving cars, GPUs are now being used extensively with companies, like car companies as well. They're getting on board. And so you have image and video processing using AI, and specialized GPUs are being created and have been created, and that's what they're being used for. And now I will show you the state of the art graphics quality that's going to be in the next generation of games starting yesterday, or like a few months ago, basically. And there's kind of some really cool things going on, and or you can say like this is the future of gaming kind of stuff. But anyway, I'd like you to take a look, and it's something fun for everyone. And it's pretty cool if you ask me. So here we go, and hopefully everyone will be able to see this. Where are you? Okay, here we go. Is it coming through okay?
Yeah. Is there supposed to be sound or not?
There's no sound? Is, can anyone hear sound?
I do not.
Just give me a second then.
This is a YouTube site, right?
Yeah.
Okay, if you just put the YouTube link in here, we can we can probably just follow up with that afterwards.
Yeah, okay, so I'll just let it play, and yeah, you guys can take a look after.
Right. Thank you. Did you display this before, Nav? Because this looks, and I mean this actually in a good way. This looks familiar.
No, I didn't.
Okay, I wonder where I saw this before.
Yeah, so the exciting thing about that is that that was done on a single GPU in real time. So that's like usually like people are like, "Oh, what's the big deal? We've seen that in movies before." So there's two things. There's one is real time and one is rendered. Oh, 1 second. And okay, so it's like so that is being done in real time where that's like an interactive game that someone created and they were playing through it and so on and so forth. So it's like really exciting about like that kind of stuff is going to be available in the near future.
Uh-huh. And how does it apply to, by the way, you mentioned AI. That was one of the things I was going to ask you about. So you kind of touched upon that. How is this applicable, this technology applicable with regard to self-driving cars?
So, okay, so AI, okay, so that's what I wanted to cover, and it has to do with the rate. I know the ray tracing question came up before. So the newest GPUs have something called RTX technology, which has to do with ray tracing. Ray tracing is like now built into the GPUs using RTX. Like so, what you saw before that was a ray trace scene that wasn't rasterized, and the way AI comes into play, so they have these things on the GPUs now called tensor cores. So you saw the diagram from before where it showed like the GPU had thousands of cores. So now it has even more cores, and it has also has something else, an additional set of processors in the GPU called tensor cores. So the tensor cores are like the GPU now has its own like kind of like subset of processors inside it that are just used for AI processing of like data. So you can put it like just like AI works with you pass in like trained data, and then it's able to using that trained data, it's able to make decisions about and predictions about like contexts of information or situational uses that what AI is designed for. And so now it's basically the same concept of AI, but it's using specialized compute power in tensor cores on the GPUs. And so the GPU that demo was running on, that's like a desktop graphics GPU. But then what NVIDIA and other companies are doing is like for the cars, they have like a smaller form factor where the they have like they spend millions and billions of dollars on the trained models. They pump those trained models into the cheaper GPU for the car, and then they run the program, and the GPU now has the capability of using the AI trained model efficiently to do its image processing, so it can detect objects and so on and so forth.
I see. Okay. So it's using this technology of graphics programming for, in a sense, instead of just displaying, turning it around for the sense of analyzing it and doing image processing.
Right, but so that section of GPU programming, that's more like GPU computing or the direct compute stuff I showed you. Like that's more like engineering, science, engineering work stuff where they have the code from the code looks more like regular code you would see on a computer. It's not really for like interactive computer graphics and like the code I was showing you. So it's the second section. It's like GPU stuff. But that code, like the AI code, even like that even looks different and is loaded into the GPU differently. But basically, the thing remains the same as far as you have a separate device, the GPU. The programming API tells the GPU, hey, you have video memory, you have processing, you have threads available. I need to use those threads for some purpose. So that's like a low level or high level way of looking at things. And so what the AI technology is just using that the additional hardware, the tensor cores, it's saying, hey, here's a programming API. Are your tensor cores available for AI usage or whatever, or for image processing or whatever the application usage is? And it's using them for, but so the way it works remains the same.
Okay, there's a question on the chat. Thank you.
All right, let me see. Yeah, exactly. So it's so they're basically Well, it's not even installing so they're specialized GPUs, like I said. So it's like, yeah, they're using the GPUs with trained models to perform AI on for car vision, like for self-driving cars and so on and so forth. Which basically what the training does is, like I said, they spend billions of dollars, but they do it once. Once you do that, once they get the trained model, they can implement that on cheap, not cheap hardware, but less expensive hardware than it would take to do the training. So that's a huge price saving there. And then that's what they and you know the GPUs in the for the cards, they take up less energy and so on and so forth as well. And so they're yeah, so they essentially that's what they're doing. Any more questions? Let me
Well,
verify the
before,
link.
be, okay, there's one, there's, okay, there's a comment here.
Oh, I love comments.
In the chat.
Yeah. Yeah, so I posted the link. Let me post another link actually. And wait, okay, so amazing. Thanks a lot for this comprehensive introduction. Yeah, thank you everyone. I enjoyed. It was great for me. It was my first time ever um, speaking on the topic. I've been doing it for a while. Like I said, I've been studying a lot. I hope to teach one day. And but so for this great opportunity for me, I really appreciate everyone attending. I hope everyone learned something um, as far as what's been going on with that and what and all the work that it entails. And next time you see a graphics programmer, buy him a coffee or a drink or something.
Hey, Nav, I wanted to say thank you for putting this together, all the effort that you put together in here. And let me share something real quickly here. Am I sharing?
I'm not sure. 1 second. I just want to put. I'm posting another video I wanted to show, but
Okay.
um, on the chat if anyone wants to take a look, and it's pretty cool. All right, and go ahead, Angelo. You wanted to share?
Yeah, if I could figure out how to do it. I am having, oh, here it is. Okay. Oops. I wanted to present this to you, Nav, for in the as a appreciation for you putting this together. Thank you.
Oh wow, that's awesome.
So thanks for putting this together. A lot of work, very interesting material. I'll look forward to learning more about it. And if there's, let me just figure out if I can unshare here. There we
Well,
go.
I didn't know I was going to get that. That's awesome.
Oh, you're welcome. Thank you. Okay, and
Angelo,
there's, yeah.
Angelo, it's Gary. It sounds like it went very well. It's not my forte, but I could tell it was a good meeting. Those of you that put this together, that's really great.
Yeah,
Thanks.
thank you very much, Gary, and Nav again. Thank you very much for putting this together.
You're welcome. And really quick, I wanted to say I couldn't have done it without everyone in the computer graphics and computing communities, as well as IEEE communities, who I know everyone has a hand in. They all kind of share and do this and that. And I'm just thrilled and overwhelmed last few decades of the amount of community support that we've received and I personally have received even. And it's truly amazing to be a part of.
When is your book coming out?
I'm writing a book.
Are you? Okay.
Yeah, on computer graphics
Excellent.
programming. Yeah,
Excellent. Excellent.
it's a textbook, and I'm focused right now on the on the movie studio and the video game studio primarily because I need to pay bills, and I've been mooching for a while, so I got to do that. Got to get that done. Got to pay some people, and you know, then we'll. But I'm writing. I'm working like crazy, like you wouldn't believe.
Well, that's great. Look for, but by the time it's published, then the field will have moved ahead to 100x more, right?
Could be. I'm updating it. It's right now. We just went through a transition as far as new technologies being introduced. So I think we're good for a while, and but it could always change. So, but things are looking pretty steady nowadays.
Okay.
Same thing with the web programming. I noticed. I don't know if anyone noticed, but like interactive graphics have become more like a lot of work was done there, and like just getting the computer graphics stuff on the web, like that, like to get it to be used inside browsers and stuff like that. So that was a lot of work, and which I was more like I'm more on the user like testing side of things. Like I make sure everything's going smooth and steady kind of thing. But I can't take credit for any of it. So, but thanks to everyone in the community. I think it's great.
Again, thank you. Are there any other comments or questions? Okay.
I'm happy to see the chapter moving with more than one meeting, you know, spring or fall. This is great.
Well, thank you. Yeah, this is excellent. There's one more comment. I appreciate holding this event online and posting it on IEEE vTools. That's how I came here.
Oh, I guess we'll post it afterwards. But yeah, everyone, I appreciate everyone attending. If they need to reach out to me if they have any additional questions or links and so on and so forth, I think I'm going to be making the slides available as well in PDF form. And so if you need to take a look at the stuff again, you know, hopefully it'll be available, and I'm pretty sure it will be.
Excellent. Okay, well, it's been a lot of material, Nav. Very interesting stuff. Again, thank you for putting this together, the effort involved in that. And I guess well, maybe was there one more question? Yeah, okay, right. I was Nav responding. So anyway, again, thank you. And you and I will be in touch for a variety of, you know, related matters, computer society stuff. Thanks for putting this together. And I guess at this point, we'll wish everybody a good night. And maybe you want to close the recording, save it. A lot of good material there. And I guess we'll be meeting again, Computer Society, in 2021.